Okay. So now we are listening to Federico talk about the efficiency of transverse forces.
Okay. Hi, everyone. Thanks for the organizer for having me here. I'm very happy to join this workshop. It's extremely instructive. So today I would like to talk about a work that I did in collaboration with Ludovic Berthier, Gregor Zamel, and my supervisor, Frédéric Van Vigeland, on the efficiency of these transverse forces in dense liquids. So, so in a word, what are the goals that we are pursuing? Well, we want to consider a system with many degrees of freedom and energy V, and the goal that you give yourself is to sample the Boltzmann distribution. Now, this is an ubiquitous problem that is hard in a set of interesting fields, like in protein folding or in optimization and machine learning. But in particular, the manifestation of this problem I'm most interested about is the case of disordered materials. So an umbrella term that covers a variety of materials that range from the atomic to the macroscopic and granular scale. And usually practitioners and experts of simulation in this field, what they aim at doing, like it was done recently by Camille Scayet, Benjamin Ghislan, and Ludovic Berthier in the study of 2022, is to be able to produce as fast as possible equilibrium configuration in order then to study the thermodynamic properties or the dynamical properties with then physically realistic dynamics. So how to sample the Boltzmann distribution? I would just retake what Tony Lelièvre said on Monday. Well, one simple way to do is to resort to an equilibrium sampling algorithm, like in this case, a overdamped Brownian dynamics, where you have your potential V, and you have degrees of freedom R in the dimension, and you simulate this overdamped Langevin dynamics. Now, the equation of motion of the probability density would satisfy a continuity equation with a certain current J. And if you wait long enough, you can write the probability distribution as your target, the Boltzmann distribution that you want to sample, plus an error that will decay in time with a certain rate that is given by the spectral gap of the associated Fokker-Planck operator, and that is the relaxation time. So this, of course, in principle, it's something that works if you wait long enough. But of course, the problem is the long enough, because in this kind of system dominated by a raged energy landscape with many minima and saddle point where the system can get stuck for a lot of time, the relaxation time can become very large. Then the question is, can we reduce the relaxation time, possibly tuning and modifying the dynamical rule of evolution? And for that, I will now connect to the field of irreversible sampling. So first of all, I would like to start from an insight from applied math, which states that if you take the usual dynamics you have for the evolution of your probability density function with a certain reversible current, the one that I showed before for the evolution of the Brownian dynamics, and you add an irreversible part with the condition that its divergence evaluated in the Boltzmann distribution is still 0, so that you ensure the correct steady state, then the dynamics is accelerated in the sense that the relaxation time, when the current is turned on, is always smaller or equal to the relaxation time of the equilibrium case. This was something that we know for 30 years, but then the problem is how to implement this kind of irreversible current that we want to add to our system dynamics. Then one possible way to do that is, of course, with lifting, to which Manon gave a very nice overview introduction on Tuesday. So we'll just briefly sketch the basic idea from the seminal paper of lifting. The idea is that, okay, imagine that I have, for example, a random walker in one dimension that can hop either to the left, either to the right with probability 1/2. Of course, in order to explore the whole line, it will take a time that is proportional to L squared, where L is the size of the chain. Now, what I can do is to add an extra degrees of freedom, this plus and minus variable, and change the dynamics of my system in the sense that when I'm in the plus state, I will hop to the right with a very high probability. And when I'm in the minus state, I will hop to the left with a very high probability. And sometimes there is a small probability that I switch from one state to the other. So this is in a sketch the main idea behind lifting, so introduce an extra degrees of freedom in your system and produce an irreversible dynamics, with the constraint, of course, that you still sample the Boltzmann distribution. What are the questions that we are interested in then is how do these kinds of non-equilibrium dynamics perform in many body systems with a large energy landscape? The problem is that, first of all, you need to choose how to implement the reversible current. And usually in lifting, and the lift scheme is the reversible current. So all the part is usually washed away or modified. And so you lose control a bit on what you're adding and what you're removing from your system. Therefore, our question is that, can we identify as an alternative to a lift scheme a form of minimal model that we can plug into the glassy dynamics in order to understand the performance of irreversible samplers? Of course, it will be just one exemplification of a case, but then we will see how to extend and what ideas can we get to extend the result that we get to a broader class of systems, the broader class of dynamical evolution algorithms. And so the dynamics we resort to is what we call transverse forces that were actually introduced even in the paper where the theorem on the acceleration was demonstrated. Basically, what happens for a degrees of freedom in an external potential is that you simulate an overdamped Brownian dynamics with a gradient descent part plus noise, and you add an antisymmetric matrix that multiplies the gradient of the potential. And what I'm taking is the antisymmetric matrix to be of order 1, for example, like with a Frobenius norm equal to 1, so that I can focus on the strength of the driving given purely by gamma. So in this case, I'm introducing an extra current inside the Fokker-Planck equation. This extra current, when evaluated, the divergence of this extra current when evaluated in the Boltzmann distribution is equal to 0, so that in the steady state, I'm sampling Boltzmann, and I'm out of equilibrium. One way in which one can show it is to compute the entropy production rate, so a measurement of the length of the arrow of time in your system, and it's positive. And when the entropy production rate is positive, you are in a situation where you are out of equilibrium. So what is the performance of this kind of dynamic? Before of going into glassy, I would like to explore with you a couple of simple examples of one particle in a potential, and then move toward the glassy systems. So the first simplest case that one can think of is how does these transverse forces perform in an harmonic well? So you take, for example, a two-dimensional harmonic well, and you look at how your dynamics perform, and what it turns out is that the relaxation time for gamma different from 0 is equal to the relaxation time at gamma equals to 0. And so therefore, if you want to relax inside a convex potential, this kind of dynamics is of no use, basically. But what you can already see is that the trajectory that you follow, here depicted in red with respect to its equilibrium counterpart, is modified in the sense that I'm performing a kind of swirling and twisting motion. And this, I want you to keep in mind this picture because it will reappear in another form when we look at supercooled liquids. And yes, actually in this case for Gaussian diffusion, there is an optimal expression for A, and is not the one that we are proposing here. But then we are not interested into the problem of a convex landscape, but we're interested into the problem of a non-convex landscape. So the next minimal model in which one can address the performance of these dynamics is the problem of barrier crossing. So that you have, in the equilibrium case, this would be simulating the motion of a particle inside the double well. And then we know that the time needed to cross the barrier is proportional to the Arrhenius factor with a prefactor that depends on the characteristic of the well where you're staying and of the curvature up to your saddle point. Now, our question is, can we understand barrier crossing with this kind of dynamics? Then, of course, I'm introducing a transverse forces, so I cannot stay just in one dimension. I need to go in 2 dimensions at least. And one way by which you can do it, if you want still to simulate the single double well, is just to, which was done by Ichiki and Ozeki in 2011. In 2015 is to duplicate your system. So I create X and Y are 2 copies of my system undergoing both inside a double well potential, and to couple the motion of these 2 degrees of freedom with an antisymmetric matrix. And then the question is, what is the relaxation time and what is the path that is taken during the barrier crossing process? For this kind of barrier crossing process, there have been modification of the Fredlin-Wenzel theory of large deviation that allow us to compute the relaxation time tau. And it turns out that is very similar to the expression given by the equilibrium case with a modification in the prefactor, where the prefactor here will be given by the modulus of the positive eigenvalue of the dynamics evaluated at the saddle point. If you evaluate this lambda plus for the case of transverse forces, you get an expression that is manifestly bigger than what you have usually at the denominator for the equilibrium case. And so it shows that considering a prefactor, the time required to cross the barrier is smaller compared to the time of it at equilibrium. But of course, you're not modifying the Arrhenius weight. So one can also work out the equation for the instanton trajectories, and basically is the same as it's made up by 2 parts. So this is in this picture, what I'm representing is the most probable path that is followed in the barrier crossing process at low temperature. And you can see that in the blue curve, in the equilibrium case, I'm traversing the double well in a straight fashion, while in the out of equilibrium case, my trajectory are modified by this transverse force, and I perform a kind of curved motion, which is the one that, and it's performing this motion that the process of barrier crossing is enhanced by the transverse forces. So much for the simple example. Now we can go to the real deal. I would like just to show you a couple of images regarding glassy dynamics to just tell you what are the measurable I'm interested in and that I'm going to compare when looking at transverse forces in dense liquids. So if you take a glassy system, like a system with particles of different size undergoing kind of overdamped Langevin dynamics, one of the way the glassiness can be manifested is if you look at how much particles move in real space. So if you measure the mean square displacement, and what you get is that as you lower the temperature, this is taken from a simulation of a binary mixer of a glass former, you get the diffusion constant reduces dramatically, and in the mean square displacement, there is a plateau that extends to long time. That suggests that what it transfers is a picture of particles that start moving at very low temperature, get trapped inside a cage, and then they are able to diffuse only after spending an extremely long time, notice the log scale here, trapped inside their local environment. Now, so this change in dynamics, there is not a manifest change in the immediate structural properties that one might look at in these cases, because, for example, here, if you look at the density-density correlation in Fourier space, you find little change, the structure factor, you find little change with temperature, even though the relaxation time is increasing by orders and orders of magnitude. So this is just a small glimpse of the glassy dynamics. Now I can introduce what are the transverse forces that I'm going to simulate for dense liquids. So what I'll simulate is an equation of an overdamped Langevin dynamics, similar to the one that I showed you before, but of course for many particles, where each particle interacts with a certain potential with its neighbors, and there is an extra antisymmetric matrix that multiplies the gradient of the potential. In this case, we chose this form for the matrix A, so that X and Y are it's the plane where the transverse forces are acting, but this is actually a quite general choice in the end. You can always show that you come back to this case up to a rescaling of gamma and a rotation of the system. So first of all, I want to show you that I'm sampling, I want to give you some proof that I'm sampling the actual Boltzmann distribution and to sketch a bit the glassy dynamics that we have in the case gamma equals 0. The sluggishness that you observe in the case gamma equals 0. So we're simulating a system of a binary mixture, a Cobb-Anderson mixture of particles interacting with this truncated Lennard-Jones potential. What I'm showing here, it's the structure factor for the system, so density-density correlation in Fourier space, at gamma equals 0 for the colors at two different temperatures, one very high and one below the temperature at which the glassy dynamic, there is the onset of the slow dynamics of the system. And what you can see is that there is a good overlap between the black curve and the colored curve, which I also use in order to calibrate my time step while integrating by using my integration scheme. On the right, you can see it's just a snapshot of the slowing down of the system in this case, as we go from the temperature of 100, where particles diffuse freely and quickly, to the temperature of 0.55, well, you can see the plateau that I was showing you in the other figure, where the dynamics is slowing down. So when we turn gamma on, what happens to the dynamics? If we look at the mean square displacement here, we have that as we increase gamma from 0 to 8 in a regime where there is the onset of slowing down has already happened, we see that for gamma equals 0, particles move and diffuse, but as I increase gamma, the diffusion constant appears to increase. So the amount by which particles are moving increases. But then the question is, how does this efficiency depend on the temperature as we cool down the system? Well, one can construct a map of the speed up by measuring the diffusion constant of the system when gamma and T, when gamma is different from 0 at a certain temperature, and divide it by its equilibrium counterpart. So here is a plot as a function of the inverse temperature. And you can see that I'm starting from a very high temperature, it's order 10 to the 4, and the efficiency rises as the temperature is decreased. So at the beginning, one might get excited because actually we get an increasing efficiency as the dynamics is slowed down. But then as we enter into the glassy regime, the efficiency decreases. And so how can we rationalize this kind of motion? How can we rationalize the fact that I'm injecting a force that is driving my system out of equilibrium, so that is displacing me from the equilibrium dynamics, but at the same time, my efficiency is looking more and more similar to the equilibrium case? Well, one can start looking at how do particles move in real space, and here is the rendering of a trajectory on the XY plane of the Cobb-Anderson mixture. So one part is, you can see that for the case gamma equal to 0, there is little diffusion of the particles, while for a case gamma equal to 100, to enhance this kind of motion, the particles perform kind of circular trajectories. Now, this kind of motion of swirling can be quantified by computing the odd diffusivity. Since we are out of equilibrium, there are transport coefficients for which the existence is allowed that previously are not diffusion cannot exist in an equilibrium system. But now that I'm out of equilibrium, there are new kinds of transport that are presumably the one that helps our system relax. Now, if I measure this quantity, what I get is that the odd diffusivity is 0 at very high temperature, which is reasonable because the thermal fluctuations are sort of washing out everything. And as the temperature is decreased, the odd diffusion goes to a constant. So what is the picture that this is actually suggesting is that the particles are swirling inside the cage formed by their local neighbor, and they don't relax. So I won't talk about, sorry? Negative. Yes, because it's just about the choice you make about the direction of rotation. Yes. So we went also through analytical approaches like dynamical mean field theory and mode coupling theory. I won't go into that. I just want to briefly sketch you that you recover a similar picture by using the mean field theory of supercooled liquids for a dilute case. And so going to the outlook and the conclusion, so the efficiency decreases in the glassy phase for this irreversible sampler. And this happens because the current that I'm inserting inside my system is uninformed. The motion of the particle is uncorrelated. They get stuck in their local cage. And then the question is, how much of this can be generalized to other irreversible samplers? How much is this decreasing of efficiency to be expected also in other form of irreversible sampler? And if not, why? Is there an optimal design for this irreversible current? What about quenching protocols? Because now I showed you just equilibrium dynamics, but in principle, one could look at also what happens when you start from a high temperature and you go down to a low temperature. Is this more effective or less effective compared to what we saw in equilibrium? And then, of course, there is more to life than glasses. What are the applications that we can, I know. Then what are the applications that we can find for other systems? Because, okay, this is an extremely hard example on which I targeted my problem, but maybe in some other context, this kind of out of equilibrium motion can be more effective. So with this, I thank you for your attention, and I'm ready to take questions.